So in the last lecture we saw complex measures and total variation associated to a complex measure, and we proved that the total variation is actually a positive measure. So it is countably additive. So we have just shown that it is countably additive. The next important result about total variation is that it is actually a finite measure. So mod mu, when mu is a complex measure, mod mu is a positive finite measure. Okay. So strictly speaking, positive infinite measures are not contained in the collection of complex measures. Okay. Only positive finite measures will be there. The positive infinite measures are not really considered as complex measures, but that's not very important, but one should keep the distinction in mind. Okay. So let us start. So far we have proved that if we have a complex measure, then we have mod mu, which is a positive measure. So the major theorem we want to prove in this session is that mod mu is a finite measure. Of course, it is a positive measure. So what does that mean? That is, so remember we have x f mu, where mu is a complex measure, and mod mu is a finite measure, meaning the total measure of mod mu is a finite number. So it is a finite positive number. Okay. So we will start with the technical lemma. Okay, so this has nothing to do with measure theory, it is a complex analysis lemma. So let us take complex numbers Z1, Z2, etc. Zn, complex numbers. Then, so there are capital N many complex numbers. Then there exists a subset, we will call that S, contained in 1, 2, 3, etc. capital N. So we are saying we can choose a subset so that some inequality is true. So what do? You look at Zk, where k in S. So S is a subset of 1 to up to n, right? So you choose some of them and take the sum of this, and that is greater than or equal to 1 by pi. Well, 1 by pi is a constant which comes out in the proof. It is not really important for our proof that mod mu is a finite measure, but there is a 1 by pi there. Okay, summation k equal to 1 to n mod Zk. Okay, so this is a technical lemma. So let us prove this first. So this is easy. So we can choose some subset, right? That is what we want to find out. Okay, so write Zk to be mod Zk. So that is the polar coordinates in the complex plane, times e to the I alpha k. Alpha k is the argument or of Zk, the angle. So alpha k so we will choose alpha k to be less than between minus pi and pi, right? That is allowed. For theta in minus pi, define, okay, let S theta. So S theta is going to be a subset of 1 to up to n. So this is all k such that cos of alpha k minus theta is positive. Okay, what is alpha k? Alpha k is the argument of Zk. Okay, well, we will see why. Okay, all this is right now, it might look arbitrary, but the proof will immediately tell you why. Now our idea is to choose a theta so that S theta will work in the lemma. Okay, so in the lemma we need this inequality. We are going to show that for some theta the S theta will work. So let us sum over S theta. Okay, k belonging to S theta, Zk, right? So k belonging to S theta Zk. So I am trying to sort of bound this, right, getting a lower bound for this. Well, this is equal to theta as of now is fixed, right. So I can multiply this with e to the I theta. Modulus of e to the I theta is 1, so it doesn't change anything. So I can say k in s theta, and the e to the I theta has nothing to do with the summation. So I put, well, e to the minus I theta zk modulus. This is of course greater than or equal to, so modulus of a complex number is greater than or equal to the real part of the complex number. So it's real part of summation k in s theta e to the minus I theta zk. Okay, so again, so far we have not done anything non-trivial, which is equal to, so what is the real part of a complex number? That is the cosine of whatever is whatever the angle is, right. But zk is mod zk times e to the I alpha k. So when I multiply by e to the minus I theta, I will have a minus theta here. So I will get mod zk to the e to the I alpha k minus theta, and when I look at the real part, I am going to get the cosine, right. So this is simply summation k in s theta mod zk, of course that will be there, and you have cos alpha k minus theta. Okay, so notice that s theta is all those k such that cos alpha k minus theta is positive. So this is a positive quantity, and I will write it in terms of the function cos. So this is k equal to 1 to n. So now I am going from 1 to n, mod z to the k. Of course all the k's don't come there, right. S theta is such that this is true. So whenever cos alpha k minus theta is less than or equal to 0, I want it to be 0. So that is precisely the positive part of the function. So I look at cos plus alpha k minus theta. Okay, so what is cos plus? Cos plus is the positive part of the function. Positive part, like f, for any measurable function we define f plus and f minus, right. So this is just the f plus, positive part of the function cos. So for whenever this is negative, I have 0. So that is why the summation is over k in s theta. Okay, but now choose, so choose theta naught such that, right. So this is some inequality, right. So some like this is greater than or equal to whatever is here. Okay, so you choose theta naught such that RHS is maximum, RHS is maximized. Okay, well, you can think of this as a continuous function if you want, and you are looking at a compact interval. So there is some theta naught for which the RHS is maximized. But then this maximum is greater than or equal to some integral. Okay, so I'll write this here. So this is greater than or equal to, so maybe I should write one more line here. So so summation k in s theta naught, okay, zk modulus is greater than or equal to summation k equal to 1 to n mod zk cos plus alpha k minus theta naught. So the right hand side is the maximum value you can get. So this is surely greater than or equal to 1 by 2 pi integral minus pi to pi, okay, d theta. So this is just 1, right. So I am only taking the maximum of the function outside. So this is, so I'll write this as summation k equal to 1 to n mod zk. Now I simply write cos plus of alpha k minus theta d theta. Okay, so think of this as a function of theta, then this is the maximum of the function, right. So that can come out, and you will have this minus pi to pi, 1 by 2 pi will give me 1, right. So this is true. So now this is easy. So this is equal to, so you calculate this integral. So you can for each theta, for each alpha k, you know how to calculate this, because alpha k cos plus alpha k minus theta is cos of alpha k minus theta when it is positive and it's 0 otherwise. So, you write down the integral, you can calculate this to get 1 by pi summation k equal to 1 to n mod z k. Okay. So, calculate this, calculate 1 by 2 pi minus pi to pi cos plus alpha k minus theta d theta. Okay. So, you will get the answer then. So, the technical lemma is done. We are trying to prove that mod mu is a finite measure. Okay. So, proof is by contradiction. So, let's see that. Okay. So, proof of the theorem. Okay. So, we are trying to prove that. So, mod mu is a finite measure, right. So, mod mu of x is finite is what we want to prove. Okay. So, suppose there exists some set E in script f such that mod mu of E is infinity. Okay. If it is not a finite measure, of course it will be infinity on some set, maybe it is infinity on the whole space, but let us start with some set E. Okay. Put some constant t equal to pi times pi, because the pi is there in that technical lemma, 1 plus modulus of mu of E. Okay. So, do not get confused, mod mu of E and modulus of mu E are different. Okay. Alright. Now, because mu E is a complex number, so mod of mu E is a finite positive quantity. Okay. So, t is a finite positive quantity. Okay. So, there exists a partition, there exists a measurable partition of E. We will write this in the finite as a finite union. It can be an infinite union, but you can cut it down to a finite union. We will see why. Such that summation I equal to 1 to n modulus of mu of EI is greater than t. Okay. Well, why is that? So, let's recall everything. Mod mu of E was defined to be supremum over summation modulus of mu of Ej, j equal to 1 to infinity, where E was written as union Ej, measurable partition, right, j equal to 1 to infinity. So, disjoint measurable sets. So, instead of choosing an infinite partition, I am choosing a finite partition, because any such sum can be approximated by a finite sum, right. So, that is the reason one can replace an infinite sum by a finite sum. Alright. Even in the definition, so this is an exercise, you can change the in the definition of mod mu, in the definition of mod mu, we may choose finite measurable partitions. Okay. So, measurable partitions. So, that means I do not need to write this as union j equal to 1 to infinity. I can go up to finitely many sets, and that will do, because any infinite sum, these are all finite quantities. So, infinite sum can be approximated by finite sums. Okay. So, that is the reason. So, Anyway, this is something which you can check. After the proof of this, it will be much clearer, because these are finite measures, so these are all finite convergence series, and so you can always approximate the infinite series by a finite series. So you will have a measurable partition with this property. So I'll leave it to you. Why we use the property of the supremum. Okay. So now, so this is like finitely many positive numbers. So complex numbers taken modulus with. So use the lemma. Use the previous lemma. Use the previous lemma to get. So if you use the previous lemma, so I'm applying previous lemma to the complex numbers mu e1, comma mu e2, comma etc. mu en. Okay, so finitely many complex numbers, right? Z1, Z2, Zn. Then I have a subset of 1 to n such that sum of these things. So I'll get a subset, let us say S, such that k in S, and I am adding these complex numbers, right? Modulus of this is greater than or equal to 1 by pi summation j equal to 1 to n or k equal to 1 to n mod mu ej. Correct? This is what we have. But the ej's are disjoint. Okay, so recall that ek are disjoint. Ek are disjoint. So this sum will become the measure of the union. Correct? So on the left hand side we will have modulus mu of union k in S ek, right, because they are disjoint, greater than or equal to 1 by pi summation j equal to 1 to n mod mu of ej, which of course is greater than or equal to t by pi, which is greater than 1. Okay, so greater than 1 is the important part. So let's see why it is greater than t by pi, because this sum is greater than t, and I have a 1 by pi here, so that will give me t by pi, and t by pi is of course greater than 1 because t is chosen like this, right? So t by pi is greater than 1. Okay. So what did we get? We got, so let's call this set A. Okay. Call this set A. Okay. So A is contained in E. Remember, E is the set we started with. Okay. And E is the set we started with. E we wrote as a finite partition, disjoint union of finitely many measurable sets, and from that there is some selection which gives us the set A, right? It is a set contained in E, right? It is union of some ej's. So what we have got is A, which is a subset of E measurable, such that mu of A is greater than 1. Okay. Now if B is the complement of A inside E, okay, then, well, what is mu of B? Mu of B is mu of E minus mu of A, correct, because A and B are disjoint, right? A, so this is, let's say this is E, I am getting some set A which is a union of ej's, and the complement is B. So measure of B is the measure of total measure minus measure of A, correct? Okay. So modulus of this will be equal to modulus of this, which is of course greater than or equal to mod mu A minus mod mu E, right? So that is always true. If I have two complex numbers, this is greater than or equal to mod W minus mod Z, or mod Z minus mod W, right? It doesn't really matter, which is of course greater than or equal to, so I know this is the set A, right? So I have t by pi here as a lower bound, okay, minus mod mu e, which is equal to 1. Okay, so this is the, I mean, you just have to remember the expression for t, right. From this, if I look at t by pi minus mod mu e, that is 1, right, because t was, remember, t was pi times 1 plus mod mu e. So t by pi minus 1, right, that is the t by pi minus mod mu e, that is just 1. So what did we do? We got A contained in E such that mod of mu A is greater than 1. The complement B also has the property that mod of mu B is greater than 1. Okay, so let us write that as a separate sentence. So we started with E such that mod mu of E is infinite. Okay, what did we do? We got E as A union B, okay, disjoint such that modulus of mu of A is greater than 1, modulus of mu of B is greater than or equal to 1, right. So I can put greater than or equal to 1, doesn't really matter. So that is a, so that we can apply again and again. Okay, so now suppose, that mod mu of x is infinity. Okay, we are trying to prove that this is finite, right, and so we are trying to get a contradiction. Suppose mod mu of x is infinity. So we have x, okay, and we can partition it to two parts, right. So I have A, which I will call A1 and I will call B1 here. Okay. So using the earlier one, we will get x as a union of A1 B1 disjoint, okay, disjoint, but importantly both of them will have modulus of their measure greater than 1, right, and so both the sets, right. This is what we just proved. For any set with infinite mod mu measure, I can disjointify them such that each portion has measure greater than or equal to 1. So I do that for mod mu x. Okay. So now one of them should have infinite measure, right. So let me write it here, mod mu x, so this is the infinity part. Well, it is a measure, so it is mod mu of A1 plus mod mu of B1, right. So one of them will have to be infinity, so we will assume that this is infinity. Okay. So I can do this with mod mu of A1 to be infinity. So I can continue. Well, if you continue, what happens? So A1 is the set which has infinite mod mu measure. I can partition it, right. So now I will get A2 and B2. Okay. So we will get A2 and B2. So A1 can be written as A2 union B2 disjoint, of course, with what is the property? We are using the previous step. If I have a set with mod mu measure infinity, I can disjointify them so that mu of A2 greater than or equal to 1, mod mu of B2 greater than or equal to 1. Okay. And of course, one of them will have to have infinite measure. So we will assume it to be A2, right, and mod mu of A2 is infinity. So we continue this, right. So continue. So what are we getting if you continue this to get a sequence A1, A2, A3 etc. Okay, so yeah, okay, I should be more careful here. So I'm writing X as A1 union B1 disjoint. I get A1 mod of mu A1 is greater than 1, mod of mu B1 is also greater than 1. Okay, so maybe the sets should be very clear. So I start with B1. So I am getting a sequence of B's rather than A's, because that is what will give me a contradiction. So B1, B2, B3 etc. right. So I have B1, I have B2, and then, well, this is the one which has infinite measure, so it decomposes it to A3 and B3. Okay, so B1, B2, B3 are disjoint, right. So this is a disjoint sequence, disjoint, okay, such that modulus of mu Bj is greater than or equal to 1 for every j, right. So at each step we have that both the pieces have measure greater than, or modulus has greater than value greater than 1. So we are getting a sequence of disjoint sets such that the measure, modulus of the measure is greater than 1. So now if you look at union Bj, j equal to 1 to infinity, let's call that B. Okay, of course this would be a measurable set. What do you know about mu B? Well, mu B, because these are disjoint, this will have to sum up, j equal to 1 to infinity mu of Bj. But this converges, so this converges, this should converge, otherwise it will not make sense, right. It converges absolutely, in fact they should converge, which implies that mu of Bj go to 0, right. Nth term will go to 0 as n goes to infinity, that if you have a convergence series. But that is not possible because modulus of mu Bj is greater than or equal to 1 for every j, so it cannot go to 0. So that is a contradiction. Okay, so we started with, let me just repeat it once more. We started with a set with mod mu equal to infinity. First thing we did was to decompose E into two sets where both of them have modulus measure greater than 1. Now one of them will have infinite measure, so you continue this. So while continuing this, you get a sequence of disjoint sets whose modulus of the measure is greater than or equal to 1. But that is not possible because the union should have the measure which is the sum, and the sum should converge, right. That is part of the definition of the complex measure, and so it should converge, the nth term should converge to 0, which will contradict whatever inequality we have got here. Okay, so let us before we finish, let's look at some examples. So or let me write this as an exercise. This is easy to do. Suppose I take my space to be the natural numbers, okay, and mu of j I take to be aj, some complex number, okay, with summation mod aj finite, okay, j equal to 1 to infinity. Okay, so what is mod mu? So mod mu, remember, is the total variation measure, right. So you can prove that mod mu. So mod mu of singletons j, right, that will do. So that is actually mod aj. You will see that this is true, and so that sort of explains why modulus is used. Okay, so if you have a function instead of numbers, you will see that modulus is coming. So let's see, we will prove later. We will prove later that if I define nu e to be integral over E f d mu, where f is in L1 mu, where mu is a positive measure, positive, if you want sigma finite, positive measure, but f can be complex valued, right? Then I know nu is a complex measure. Mod nu is given by mod f. So mod f is a positive function, right? Since f is in L1, this is a finite measure. Okay, so mod nu is a finite measure, which we know, right, in general, because f is in L1, right? But that's not, it's true in general, so let's rub it off. So this we will prove later. Okay, so that is why the modulus, in a sense, the modulus sign or the notation is justified because of this. And this sort of measures form a rather important class, which we will see soon. So let us let's just look at the space of, so if I have a space X and I have a sigma algebra F, the collection of complex measures, let's say I have two complex measures, mu and lambda, complex measures. Okay, then I can add them, right? So define mu plus lambda. So this is a new complex measure to be mu of E plus lambda of E, right, for any E in. So this makes sense. So for every E in script f, then mu plus lambda is a complex measure. Then mu plus lambda is a complex measure. That is trivial, because all that you have to do to check is if Ej's are disjoint, mu plus lambda of Ej will be, union Ej will be the sum, right, but that happens for each term. Similarly, you can multiply. So if I take a complex number now, alpha, then alpha times mu, if you define this to be alpha times mu of E, right, so that is also a complex measure. Okay, then alpha mu is also a complex measure. So what we have just proved is the space of complex measures is a complex vector space. So let us, so if I have xf, yeah, the class of complex measures is a complex vector space. It's a complex vector space. Okay, so we will stop here. We have just proved that the total variation measure is actually a finite measure. So associated to any complex measure mu, we have mod mu, which is the total variation measure, and that is a finite measure. We will continue with complex measures in the next lecture as well. The major result which we will prove in the next few lectures is the Radon-Nikodym theorem, which actually characterizes the measures which we had written down. So recall that we wrote down nu of E to be integral over E f d mu. Such measures have a certain property which is called the absolute continuity property, which is what we will define in the next session, and we will classify such measures. That is what is known as the Radon-Nikodym theorem. Okay, so we will stop here.